Uranus might be the most underestimated planet in the solar system. Not because it lacks interesting features, but because nearly everything we thought we knew about it is turning out to be incomplete, and in some cases, wrong. Here is the situation. Uranus has been visited by exactly one spacecraft ever. Voyager 2 flew past on the 24th of January, 1986, spending just a few hours in close proximity before racing on toward interstellar space. For nearly 4 decades, the scientific community has worked almost entirely from that single encounter. No follow-up missions, no new close observations, just one brief pass from a craft that couldn't slow down. And yet, in the last several years, a wave of new research has fundamentally changed our picture of the seventh planet. New telescope technology, fresh analysis of old Voyager data, and sophisticated computer simulations have revealed a world that is far more dynamic, far more violent in its past, and far more structurally uncertain than anyone previously understood. Some of these findings don't just add detail to what we know, they question whether we had the basics right in the first place. One of those basics is the most fundamental thing you can say about a planet. What is it made of? Uranus has long been grouped with Neptune under the label ice giant. The standard model describes a small, rocky silicate core at the center, surrounded by a deep mantle composed of water, ammonia, and methane in a semi-fluid, compressed state. The word ice is misleading here. The temperatures deep inside Uranus can reach nearly 5,000 degrees Celsius, and the pressures at the base of the mantle climb to around 600 gigapascals. Under those conditions, the molecules don't freeze. They behave more like a dense, hot ocean than anything you'd find in a freezer. The pressures in that mantle are so extreme that they can break apart methane molecules entirely, stripping out the carbon atoms and compressing them until they crystallize. The implication is that it may literally rain diamonds deep inside Uranus, forming and sinking toward the core. It's a striking image, and it has been part of the standard description of ice giant interiors for years. But a study published in the journal Astronomy and Astrophysics in 2025 significantly complicated this picture. Researchers Luca Morf and Ravit Held at the University of Zurich approached the problem differently from previous work. Rather than starting with assumptions about what Uranus contains and checking whether the observations match, they took what they called an agnostic approach. They generated a large set of randomized interior models, covering a wide range of possible compositions and structures, and then filtered them against what we can actually observe about Uranus from the outside. Gravity measurements, radius, mass, atmospheric readings. The result was unexpected. The range of compositions that remain consistent with the observational data is far broader than the standard model suggests. The ratio of rock to water inside Uranus, for instance, could be as low as 0.04. That would make Uranus almost entirely water. Or it could be as high as 3.92, which would make it predominantly rock, with very little water at all. That second possibility carries a significant implication. If Uranus is mostly rock, it isn't an ice giant in any meaningful sense. It would be what the researchers call a rock giant, and that would challenge the models we use to understand how planets form in the outer solar system. The formation models currently in use suggest that planets in the outer solar system gather their bulk primarily from icy material, the frozen compounds that are abundant far from the sun's heat. If a planet like Uranus is mostly rock, those models need revision. The solar system's outer regions would have had to have a different composition than we assumed, or the process of planetary accretion would have worked differently than we've modelled it. The authors are careful to note that this is theoretical work. They are not claiming to know what Uranus is made of. They are pointing out that the current data doesn't tell us as conclusively as we thought. Resolving the question requires a mission that can make direct measurements, something no spacecraft has done since Voyager 2 in 1986. Setting aside the question of internal composition for a moment, the outer layers of Uranus are better understood, though still not fully. The atmosphere is composed mostly of hydrogen and helium, with about 2% methane. That methane is responsible for the planet's distinctive appearance. Methane molecules absorb red and orange wavelengths of light, and what bounces back is the blue-green color that Uranus is recognized by. If you removed the methane, the planet would look more white, like a giant cloudy ball of hydrogen gas. Voyager 2's pass through the Uranian system in 1986 showed a planet that looked remarkably featureless, calm, almost blank. A few faint cloud structures were visible, and there was one small dark spot, but the overall impression was of a world without the turbulent activity seen on Jupiter or Saturn. Scientists at the time took this as consistent with Uranus being something of a quiet, sluggish planet. That interpretation didn't survive contact with better telescopes. In 2014, the W.M. Keck Observatory in Hawaii picked up 8 massive storms in Uranus's northern hemisphere. These were not minor disturbances. One of them, the largest white feature visible in the near-infrared image taken at 2.2 microns wavelength, was about twice as bright as anything previously recorded on the planet at that wavelength. It accounted for roughly 30% of all the light reflected by the planet in that entire observation. Storms of that intensity are not subtle features. They are enormous atmospheric events, and they had been invisible to Voyager 2 simply because that spacecraft lacked the right instruments and opportunities to detect them. Something important follows from this. The apparent tranquility of Uranus in 1986 was partly an artifact of the instruments available, partly the limitations of a single flyby, and partly genuine. Uranus is less atmospherically active than Jupiter or Saturn, but it is not inert. It is a dynamic atmosphere, and understanding what drives it requires understanding the broader context of how the planet works. A key part of that context is seasonal change, and Uranus has the most extreme seasons in the solar system. This comes directly from the planet's axial tilt. Uranus rotates on an axis that is tilted about 97.77 degrees relative to its orbital plane. For comparison, Earth's axis is tilted at 23.5 degrees, and that modest tilt is responsible for the seasons we experience. Neptune, the planet with the next highest tilt in the solar system, sits at around 28 degrees. Uranus is nearly on its side. The consequence is that each pole of Uranus faces the Sun continuously for 42 Earth years, then spends the next 42 years in complete darkness. One full orbit around the Sun takes 84 Earth years. Since its discovery in 1781, only about 2.9 of those orbits have been completed. Uranus won't have a new year again until 2033. During a Uranian summer at one pole, the equatorial regions receive far less sunlight than the polar region currently facing the Sunday. This is the only planet in the solar system where the poles regularly receive more solar energy than the equator. The seasonal implications of this are profound, and we are only now beginning to understand them properly. Hubble Space Telescope observations spanning 20 years revealed direct evidence of this seasonal process in action. Over 4 observation windows, scientists tracked how Uranus's atmosphere changed as it moved through northern spring toward northern summer, which it will reach around 2030. The North Pole, which was relatively dark in 2002 images, had become highly reflective and aerosol-rich by 2022. Meanwhile, the South Pole was darkening as it moved into the long polar winter. What this shows is that sunlight is actively controlling the structure of cloud layers and aerosols in the Uranian atmosphere. When sunlight hits a polar region, the chemistry changes. Aerosols thicken and accumulate. Circulation patterns shift. The atmosphere responds in measurable ways. And sunlight isn't the only external driver. Researchers at Imperial College London found that the Uranian thermosphere, the outermost atmospheric layer, is heated not just by the sun's light, but by the pressure of the solar wind itself. This is something that doesn't seem to happen anywhere else in the solar system in the same way. The Sun constantly emits a stream of charged particles, and at Earth and other planets, the magnetosphere typically deflects most of this. At Uranus, the strange geometry of the magnetosphere allows the solar wind to interact with the thermosphere more directly. Since solar wind pressure has been decreasing since roughly 1990, Uranus has been gradually cooling as a result. That external heating is a small part of the overall picture. The bigger question is the planet's internal heat, or more specifically, the near total absence of it. Jupiter, Saturn, and Neptune all radiate significantly more heat than they receive from the Sunday. This internal heat is a relic of the process of planetary formation. When a planet coalesces from a cloud of gas and rock and ice, the gravitational energy released by all that material falling together is converted to heat. These planets are, in a sense, still slowly cooling from their formation billions of years ago, and the heat they release drives the powerful atmospheric dynamics they're famous for. Saturn emits roughly 1.7 times the energy it receives from the Sunday. Neptune emits more than twice what it receives. Jupiter is in a similar range. Uranus emits only about 15% more energy than it receives. That is an extraordinarily low number. For all practical purposes, the planet is not releasing significant internal heat. Two studies published in 2025 confirmed that this low heat flux is real, not a measurement artifact. Uranus does have internal energy, but it is holding on to it. Something inside the planet is acting as an insulator, trapping heat deep in the interior rather than allowing it to escape upward through the atmosphere. This connects directly to what is now believed to be the most transformative event in Uranus's history. Between 3 and 4 billion years ago, while the solar system was still relatively young and chaotic, the prevailing hypothesis is that Uranus was struck by a large impactor. High-resolution computer simulations developed by Jacob Kegereis at Durham University, published in the Astrophysical Journal in 2018, modeled more than 50 different collision scenarios in an attempt to reproduce the Uranus we observe today. The results pointed to a single likely scenario. Uranus was hit by a protoplanet 2 to 3 times the mass of Earth, probably a body composed of rock and ice. The impact was not head-on. It was a glancing blow, the kind that maximizes the rotational effect. Within just a few hours, enough energy was delivered to tip Uranus's rotation axis nearly onto its side, permanently altering the planet's relationship with the Sun and setting off a chain of consequences that are still visible today. When the impactor struck Uranus, most of it didn't bounce off. The bulk of the impactor's material was deposited into Uranus's interior, particularly into the icy mantle layer. This created what the simulations describe as a hot, high-entropy shell within the planet's interior. Entropy is a measure of disorder, and high-entropy materials are highly disordered at the molecular level. These materials are poor conductors of heat. They don't transfer thermal energy efficiently. The result is that this shell, still present deep inside Uranus billions of years later, acts as an insulating barrier. Heat generated in the deep interior is trapped below it. It cannot flow upward efficiently. This explains why Uranus releases so little internal heat, why it is the coldest planet in the solar system at -224 degrees Celsius in its upper atmosphere, and why it lacks the vigorous internal convection that drives Jupiter's and Neptune's weather systems. In a very real sense, Uranus is running cold because of a collision that happened when the solar system was still being assembled. The same collision may also explain the strange geometry of the planet's magnetic field. On Earth, the magnetic field is generated by convection in the liquid outer core, where molten iron circulates in large loops driven by the temperature difference between the hot inner core and the cooler mantle above. The field this produces is roughly aligned with Earth's rotation axis, tilted only about 11 degrees away from the geographic poles. Uranus's magnetic field is not like this. Voyager 2 discovered that the field is tilted almost 59 degrees from the rotational axis, and that the center of the field is offset from the planet's geometric center by about 1/3 of the planet's radius. The field doesn't come from the center. It comes from somewhere inside the mantle, and it is strongly asymmetric. One possibility is that the impact-deposited shell disrupted the normal convective processes in the mantle, fundamentally altering how and where the magnetic field is generated. If the field originates primarily from convecting material in the mantle rather than from a central core dynamo, the irregular geometry would make sense. The deposits left by the ancient collision could be shaping the magnetic field of Uranus to this day. There is more to learn about this magnetosphere. Voyager 2 observed it during what turned out to be an unusual period. Analysis of the original data by Jamie Jasinski at NASA JPL, published in Nature Astronomy in 2024, found that when Voyager 2 flew past, Uranus was experiencing intense space weather. The solar wind was compressing the planet's magnetosphere, making it appear smaller and less extended than it normally would be. The actual magnetosphere, under normal conditions, is larger and more variable than Voyager 2's data implied. The asymmetric magnetosphere creates auroras unlike those anywhere else in the solar system. On Earth, auroras occur near the geographic poles because charged particles from the solar wind follow the magnetic field lines down into the atmosphere at the magnetic poles, which are close to the geographic poles. On Uranus, because the magnetic and rotational axes are so misaligned, auroras can appear at almost any latitude. They form sprawling, irregular patterns across the planet's disk rather than concentrated rings at the poles. These auroras have been studied extensively by Hubble in visible and ultraviolet light. By tracking the motion of auroral features over a decade of observations, scientists were able to calculate Uranus's rotation rate with a precision 1,000 times greater than what was possible from Voyager 2 data alone. The planet completes one rotation in 17 hours, 14 minutes, and 52 seconds. That is 28 seconds longer than Voyager 2's estimate, which doesn't sound like much, but when you're planning a mission to rendezvous with a moving planet, even small errors in rotation rate accumulate into significant navigational problems over time. In 2023, infrared auroras were detected on Uranus for the first time after 30 years of searching, using the Keck 2 telescope in Hawaii. The detection required 3 decades of advances in infrared instrumentation to achieve. Their presence tells scientists about the energy balance in the upper atmosphere and confirms certain properties of the magnetosphere that had been difficult to verify indirectly. The violent collision that tipped Uranus onto its side did more than reshape the planet itself. It also determined the architecture of its moon system. At the time of impact, the major moons of Uranus had not yet formed. The planet was surrounded by a disk of material, debris from the planet's own formation and from the outer regions of the early solar system. When the impactor struck, it added more material to this disk. As the debris gradually clumped together under gravity over millions of years, it formed the moons we observe today. But because the impact had already tilted Uranus's rotational axis so dramatically, the gravitational field that governed where these moons could form was itself tilted. The moons inherited the tilt of the planet and orbit in the same extreme plane, essentially circling Uranus above its equator, which means they orbit nearly perpendicular to the plane of the solar system. The 5 major moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are composed primarily of water, ice, and rock. All of the Uranian moons are named after characters from English literature, primarily from Shakespeare and Alexander Pope, which gives the system a distinctly literary quality, entirely absent from any other planetary neighborhood. Studies published in 2025 found hints that some of these moons may have differentiated interiors, meaning they may have separated into layers with rocky cores, liquid water, oceans, and icy outer shells. If true, the presence of subsurface liquid water raises questions about the potential for biological chemistry in environments far from the Sunday. These are questions that current remote observation cannot answer. Only a spacecraft that can enter orbit and study the moons in detail could provide the data needed to address them. As of the beginning of 2025, Uranus has 29 confirmed moons. 2 have been discovered recently. The 28th, provisionally designated S/2023U1, was found in 2023 by astronomer Scott Shepard using the Las Campanas Observatory in Chile. The 29th was confirmed in February 2025 using the James Webb Space Telescope's near-infrared camera. Designated S/2025U1, it has not yet received an official name. Uranus also has a ring system, though it is nothing like Saturn's. The rings are aligned with the planet's tilted axis, which means that when Voyager 2 approached in 1986, they were oriented almost directly toward the spacecraft, appearing as a nearly circular bullseye rather than the broad sweeping disk Saturn presents. 13 rings have been confirmed through a combination of Voyager 2 observations and subsequent imaging by Hubble, the Keck 2 telescope, and the James Webb Space Telescope. The most striking property of Uranus's rings is how dark they are. They have an albedo, a measure of how much light they reflect, of less than 2%. That makes them among the darkest material in the solar system. The exact composition is not definitively known. The most likely candidate is water ice that has been chemically altered, perhaps darkened by long-term exposure to radiation, mixed with organic compounds, or methane ice that has been effectively charred black by the same processes. The rings are also very young by solar system standards. Estimates suggest they formed only about 600 million years ago, which is roughly an eighth of the solar system's current age. They are thought to have formed when a small moon was disrupted, either by a collision with a meteoroid or by a comet impact. The resulting debris gradually spread into the ring structures we observe today. What is difficult to explain is why many of the rings are so narrow. Rings in space tend to spread. The particles that make them up follow slightly different orbits and gradually disperse. In Saturn's ring system, some rings are kept narrow by small shepherd moons orbiting just inside and outside the ring, whose gravitational influence corrals the material into a confined band. A few of Uranus's rings have candidate shepherd moons, but most do not have an obvious explanation for their narrowness. The mechanism keeping them confined remains an open question. One of the most productive ways to study Uranus's rings and atmosphere remotely is through stellar occultations, events in which Uranus passes in front of a distant star and briefly blocks its light. As the ring edges, the atmosphere and the planetary disk move across the star. The timing and pattern of the dimming encode detailed information about the ring positions, ring widths, and the vertical structure of the atmosphere. It was during exactly such an event, in 1977, that the ring system was discovered at all. Astronomers observing a star occultation noticed that the star dimmed briefly before and after being hidden by the planet itself. The symmetrical pattern of dips was inconsistent with atmospheric refraction and could only be explained by a ring system. A rare occultation occurred again in April 2025, when Uranus passed in front of a star located roughly 400 light-years away. In anticipation of this event, scientists organized the largest coordinated observation of Uranus since Voyager 2's 1986 flyby. Led by planetary scientists at NASA Langley Research Center, a team of more than 30 astronomers across 18 observatories around the world simultaneously observed the event for approximately 1 hour. The ring data from this campaign has already produced results. By precisely measuring the timing of each ring's occultation of the background star, researchers were able to refine the known position of Uranus in its orbit by around 400 kilometers. That might seem like a small adjustment, but it is critically important for mission planning. Sending a spacecraft to a planet you haven't visited in 40 years requires knowing exactly where it will be when the spacecraft arrives, and that means knowing its orbital position to high precision. Atmospheric results from the 2025 occultation are still being analysed, but the event marks something else as well, a clear demonstration of what international coordination can achieve even without a spacecraft at the planet. And this is only the beginning of a period of unusually favourable conditions for studying Uranus through occultations. Over the coming decade, Uranus will be positioned between Earth and the galactic centre of the Milky Way, an extraordinarily star-rich background. This alignment creates prime conditions for additional occultation studies, with what scientists expect to be the best opportunity of all, arriving in 2031. That timing is significant for another reason. The 2024 Planetary Science Decadal Survey, which sets priorities for United States planetary science missions over a 10-year period, identified a Uranus orbiter and probe as the top planetary priority for the coming decade. This is not a minor endorsement. It means that when NASA allocates funding for new flagship missions, Uranus is at the front of the line. The optimal launch windows for such a mission are in 2031 and 2032. These windows are favourable because a spacecraft launched during this period could receive a gravitational assist from Jupiter, using the gas giant's gravity to accelerate and redirect the trajectory toward Uranus. This kind of gravity assist, similar to the maneuver used by Voyager 2, significantly shortens the travel time and reduces the fuel requirements. Without it, the journey to Uranus takes considerably longer. Miss the window, and the next opportunity years later would require a more demanding trajectory. China's National Space Administration has also proposed a mission to Uranus, designated Tianwen-4, reflecting growing international interest in the outer solar system that extends well beyond NASA. The mission objectives being discussed for a Uranus orbiter are extensive. The spacecraft would map the planet's gravitational field in detail, providing a direct way to constrain internal structure models and potentially resolve the rock giant versus ice giant question. It would track the magnetic field over time, allowing scientists to understand how that strange, offset, tilted magnetosphere varies through the planet's rotation and with the solar cycle. It would study atmospheric composition and weather systems in depth, examining the cloud structures and circulation patterns that ground-based telescopes can only partially resolve. The moons would receive dedicated attention. A spacecraft in Uranus orbit would be able to make repeated flybys of Miranda, Ariel, Umbriel, Titania, and Oberon, measuring surface compositions, interior structures, and thermal properties in far greater detail than any remote observation can provide. If those hints of subsurface oceans hold up under closer scrutiny, the question of habitability moves from theoretical speculation to something that can be directly investigated. The rings, too, would be examined from up close. A spacecraft could observe the rings in reflected sunlight and in thermal emission, study their composition directly, and search systematically for the shepherd moons or dynamical mechanisms responsible for their narrowness. What is remarkable about the current state of Uranus science is how much has been accomplished without a dedicated mission. Every significant development of the past several years has been achieved either through remote observation with increasingly powerful telescopes, through new analysis of data collected during a few hours in 1986, or through computational modelling. The James Webb Space Telescope has contributed substantially, as have Hubble and the Keck Observatory. The 2025 occultation campaign demonstrated the value of coordinated multi-telescope observation. But all of these approaches have limits. Some questions simply cannot be answered from a distance. The internal structure of Uranus, the detailed composition of its rings, the presence or absence of subsurface oceans on its moons, the full three-dimensional behavior of its magnetosphere, all of these require a spacecraft that can spend time in orbit, making repeated observations from close range. The history of solar system exploration shows what happens when that kind of mission arrives. Before Cassini reached Saturn in 2004, Saturn was reasonably well understood in broad outline. After more than 13 years in orbit, the picture was transformed beyond recognition. Geysers on Enceladus, Titan's hydrocarbon lakes, the intricate structure of ring systems, the detailed dynamics of the upper atmosphere. None of that was visible from Earth or from the brief Voyager flybys. Uranus, visited only once and only briefly, has much more to give. The recent discoveries, precisely because they raise so many new questions, make the case for a dedicated mission more compelling with each passing year. We don't know whether Uranus is an ice giant or a rock giant. We don't know whether its moons have liquid oceans beneath their icy surfaces. We don't know the exact mechanism maintaining those narrow rings. We don't know whether the magnetosphere's extreme asymmetry is fully explained by the ancient impact hypothesis, or whether something else is at work in the deep interior. We don't fully understand how the high entropy shell left by the ancient collision interacts with the deeper layers over geological time. These are not small gaps. They are fundamental uncertainties about a world that is, in many ways, the most structurally unusual planet we know of. A planet that rolls on its side, that is colder than any other despite having the fourth largest mass in the solar system. That has a magnetic field centered nowhere near its middle. That may not even belong to the category of planet we placed it in. The window for a Uranus mission is opening. The planetary science community has identified it as the highest priority. The technology exists to build the spacecraft. The launch window opens in 2031. What happens next will determine whether Uranus remains the solar system's best-kept mystery, or finally becomes a world we actually understand. There is a deeper irony embedded in Uranus's story. Of all the outer planets, it is the one we might have understood best, because Voyager 2 passed closer to it than to Neptune and spent more time near it than expected. And yet Uranus remains the least known of the four giant planets, because the instruments of 1986 were not designed for what the planet actually turned out to require, and because no one went back. That decision not to return was partly financial, partly a matter of competing priorities, and partly a reflection of Uranus's reputation as the quiet, uneventful member of the giant planet family. The atmospheric tranquility Voyager 2 observed reinforced a perception that Uranus offered less to discover than Jupiter or Saturn. That perception, as it turns out, was entirely wrong. Begin with the tilt itself, because it is one of the most unusual single facts about any object in the solar system. Every planet has an axial tilt. Earth's is 23.5 degrees. Mars is similar. Jupiter is only about 3 degrees, nearly perfectly upright. Saturn sits at about 26 degrees. Neptune, as mentioned, is about 28 degrees. These planets spin like slightly leaning tops. Uranus rolls. Its north pole points almost directly toward the Sun for half of each orbit. Then its south pole does the same for the other half. No other planet in the solar system has an axial tilt above 30 degrees, with one borderline exception. Pluto's tilt is about 122 degrees, technically higher, but Pluto is far smaller and is no longer classified as a full planet. Among the 8 major planets, Uranus stands alone. For most of human history, we didn't even know this. Uranus was discovered by William Herschel in 1781, more than 2 centuries after the invention of the telescope. It was the first planet discovered through a telescope rather than visible to the naked eye. Herschel initially thought it might be a comet. He was observing from his garden in Bath, England, using a reflecting telescope he had built himself. When he tracked the object over several nights and noticed it had a disc-like appearance rather than a point of light, and that it was moving with respect to the background stars, he recognized he had found something extraordinary. At that moment, the known solar system doubled in size. The boundary of the planetary system, previously thought to end at Saturn, suddenly extended far beyond. Herschel spent years arguing for naming the planet Georgium Sidus, meaning the Georgian star, in honor of the reigning British monarch, King George III. The astronomical community outside Britain was less enthusiastic about this choice. Johann Bode, a German astronomer, proposed Uranus, the name of the ancient Greek deity of the sky and the father of the Titans. That name gradually won out, and by the mid-19th century, Georgium Sidus had essentially disappeared from astronomical literature. Even after the planet was identified and named, its extraordinary tilt wasn't immediately apparent. The geometry of the orbit and the subtlety of the axial measurement made it difficult to determine from early telescopes. The true magnitude of the tilt became clearer only through increasingly precise measurements over the following century. By the mid-20th century, astronomers were reasonably confident Uranus was tilted well beyond any other planet. But the precise value of 97.77 degrees came from Voyager 2 data. That tilt raises a question that planetary scientists have been working to answer for decades. How did it happen? Planets form from rotating disks of gas and dust around young stars. The general consensus from theories of planetary formation is that planets should end up spinning roughly in the same direction as the disk they formed from, with relatively modest tilts. A tilt of nearly 98 degrees doesn't emerge naturally from standard formation processes. Something must have changed it. The leading hypothesis, supported by the computer simulations developed by Jacob Kegerais and colleagues at Durham University, is that Uranus was struck by a massive body early in the solar system's history. The simulations modeled more than 50 different impact scenarios, varying the size and composition of the impactor, the angle of impact, and the state of Uranus at the time of impact. The goal was to find a scenario that could reproduce the three defining characteristics of the modern Uranus: the extreme axial tilt, the low internal heat flux, and the unusual structure of the magnetic field. The scenario that best fit the observations involved a body 2 to 3 times the mass of Earth, likely composed of rock and ice, striking Uranus at an oblique angle. The word oblique is important here. A direct, head-on impact would transfer maximum energy into heating and disruption. A glancing blow transfers a large fraction of its energy into angular momentum, spinning and tilting the target. The simulations showed that an oblique impact by an Earth mass or larger object could reorient Uranus's spin axis to its current position over a period of just a few hours. The planet did not gradually lean over through some slow process. The best model suggests that a single event, brief in cosmic terms, transformed Uranus's fundamental orientation. The material from the impactor didn't simply scatter into space. The models show that most of the impactor's mass was absorbed into Uranus's interior, specifically into the region of the mantle. This deposited material formed what the simulations describe as a hot, thermally disordered shell within the mantle. Think of it as a layer of material that is physically mixed and structurally disordered at the molecular level, in a way that makes it resistant to the conduction and convection of heat. In physics, the concept of entropy describes the degree of disorder in a system. High entropy materials are highly disordered, and disordered materials, at the molecular level, are inefficient at conducting heat because the orderly vibrations that carry thermal energy through a crystalline lattice are disrupted. A high entropy shell inside Uranus acts like thermal insulation. Heat generated below it by the slow radioactive decay of heavy elements, and the residual heat left over from the planet's formation, accumulates below the shell rather than flowing outward. This explains two otherwise puzzling observations simultaneously. It explains why Uranus is so cold at the top of its atmosphere, because the heat from inside cannot escape efficiently. And it explains why the upper atmosphere lacks the vigorous convection that drives the dramatic weather on Jupiter and Saturn, because convection requires that warm material rise and cool material sink, a process that requires internal heat to reach the upper layers. The irony is that Uranus is not actually a cold planet in any simple sense. The deep interior may be quite hot. It is a planet that has been thermally sealed by the consequences of an ancient violence. The collision hypothesis also provides a framework for thinking about the magnetic field. In planets with conventional magnetic fields, the field is generated by a process called dynamo action, in which electrically conducting fluid flows in complex, circulating patterns driven by heat escaping from a hot core. The geometry of the field is largely determined by the geometry of the flow, and in most planets, the dominant flow patterns align with the rotation axis, producing a field that is roughly aligned with the poles. Uranus's magnetic field is tilted almost 59 degrees from the rotation axis and offset from the planet's center by roughly 1/3 of the planetary radius. The field is not centered on the planet. It does not point toward the poles. It is as if the generator responsible for the field is located off to one side of the planet's interior and oriented in a way that has nothing to do with the planet's spin. One explanation for this is that the dynamo responsible for the magnetic field is not in the deep core at all, but in the mantle. In a planet where the mantle contains substantial water and ammonia under high pressure, these fluids are electrically conducting, and they could generate a magnetic field through convective motion in the same way a metallic core does elsewhere. If the convecting region is irregular, influenced by the high entropy shell deposited by the ancient impact, the resulting magnetic field would also be irregular and asymmetric. This is speculative, but it is consistent with what we observe. The magnetic fields of both Uranus and Neptune are significantly more complex and asymmetric than those of Jupiter, Saturn, or Earth. The ice giants appear to generate their magnetic fields differently. Understanding why is one of the key goals of any future Uranus mission. The behavior of the magnetosphere also interacts with the solar wind in ways that are specific to Uranus's unusual geometry. Because the magnetic field is so strongly tilted relative to the rotation axis, the orientation of the magnetosphere with respect to the solar wind changes dramatically as Uranus rotates. On Earth, the magnetosphere presents a relatively consistent face to the solar wind. On Uranus, the magnetosphere rotates into and out of configurations where it is more or less open to the solar wind on timescales of hours. The planet's magnetosphere literally flaps open and closes like a valve as Uranus spins. This has been described as creating a dynamic that is unique in the solar system. Solar wind particles can enter the magnetosphere much more easily during certain phases of Uranus's rotation, and the resulting interactions drive aurora patterns that are, as described earlier, not confined to the poles, but can appear at almost any latitude. The detection of infrared auroras in 2023, after 30 years of searching, added an important dimension to this picture. Infrared auroras are generated by hydrogen ions in the upper atmosphere that are energized by interactions with the magnetosphere. Their detection confirmed that the heating of the upper atmosphere by magnetospheric processes is ongoing and measurable. The techniques used to detect these infrared auroras, developed over decades of incremental improvement in infrared detector technology, represent a fundamental advance in remote sensing of the outer solar system. It is worth stepping back for a moment to consider what the James Webb Space Telescope has contributed to Uranus science in just its first few years of operation. The James Webb Space Telescope was launched in December 2021 and began science operations in 2022. It was designed primarily to study the distant universe, observing the first galaxies formed after the Big Bang and characterizing the atmospheres of exoplanets. But its sensitivity and infrared capabilities have made it a remarkably powerful tool for studying objects within the solar system as well. Images of Uranus taken by James Webb revealed the ring system in extraordinary detail, showing structures that were not visible in previous Hubble images. The James Webb images captured not only the 13 known rings, but also subtle brightness variations within them that were not previously measured. The James Webb Space Telescope was also used to confirm the 29th moon in February 2025, using its near-infrared camera to detect a body too faint for previous instruments. For atmospheric science, the James Webb Space Telescope's spectrographic capabilities allow it to identify chemical signatures in Uranus's atmosphere with greater precision than any previous instrument. Ongoing analysis of James Webb data is expected to refine our understanding of the distribution of methane, hydrogen sulfide, and other compounds in different atmospheric layers, providing data that will be compared with future in situ measurements from a dedicated probe. One of the things that makes outer solar system science so challenging is the sheer distance involved. Uranus is, depending on where both planets are in their orbits, roughly 2.7 to 3 billion kilometers from Earth. At the speed of light, a signal takes between 2.5 and nearly 3 hours to travel one way. This means that controlling a spacecraft in real time is effectively impossible. Every command sequence must be planned in advance. Every decision made remotely. The spacecraft must be capable of autonomous operation over extended periods. This technical challenge is manageable with current technology, but it means that the science return from a mission depends heavily on how the mission is designed before it launches. Getting the instrument suite right, the orbital parameters right, and the observation sequences right requires deep knowledge of the target, which is itself incomplete for Uranus. The scientific community is trying to prepare for a mission to answer questions while simultaneously still formulating those questions. The composition debate is a good example. If a future mission carries a gravity science instrument capable of measuring the gravitational field of Uranus in 3 dimensions as the spacecraft orbits, the field's shape will reveal something about the internal density distribution which constrains the internal composition. But how to interpret that data depends on models that themselves contain uncertainties. The information from a gravity measurement will likely refine the models, rather than definitively resolve the rock giant versus ice giant question in a single observation. A probe dropped into the atmosphere would provide direct measurements of chemical composition at various atmospheric depths, including the abundances of noble gases like helium, neon, argon, and xenon, which carry information about the conditions under which Uranus formed. The noble gas abundances in Jupiter's atmosphere were measured directly by the Galileo probe in 1995, and those measurements significantly constrained models of Jupiter's formation and of the composition of the early outer solar system. A similar measurement at Uranus would be enormously valuable for comparative planetology, the study of how the planets as a group form and evolve. Understanding the ice giants is also directly relevant to understanding planets outside our solar system. Over the past 3 decades, the Hubble Space Telescope and the TESS satellite have found thousands of planets orbiting other stars. Among the most common types discovered are planets with radii between 1.5 and 3 times that of Earth, which are thought to be similar in general character to Uranus and Neptune. These sub-Neptunes and mini-Neptunes, as they are informally called, appear to be extremely common in the galaxy. Our solar system has 2 ice giants that we can study in detail. Every measurement we make of Uranus and Neptune teaches us something about the most common type of planet in the Milky Way. In this sense, Uranus is not just a curiosity in our own backyard. It is the nearest example of a class of planet that dominates the galaxy's census of worlds. Understanding how it formed, what it is made of, how its atmosphere works, and how its moons developed is directly relevant to understanding the structure and variety of planetary systems across 100 billion star systems. The 2025 occultation campaign provides a vivid illustration of what coordinated international science can accomplish even without spacecraft hardware at the target. 30 astronomers at 18 observatories simultaneously observed Uranus for 1 hour. Each observatory recorded the precise timing of when the planet, its atmosphere, and each ring obscured the background star. By combining these timing measurements from multiple locations around the world, triangulating the geometry of the event, scientists were able to refine the positional data for Uranus with a precision that no single telescope could have achieved. This kind of coordination, while impressive, is still fundamentally limited compared to what an orbiting spacecraft provides. Occultation observations are possible only when the geometry happens to be favorable. They last for a fixed, short window. They are constrained by what can be measured through the process of a shadow passing across a star. An orbiting spacecraft can make equivalent measurements continuously from multiple angles over years, in configurations that no Earth-based telescope can replicate. The preparation work being done now, refining the orbital position of Uranus, characterizing its atmospheric structure with James Webb, studying its ring dynamics through careful observation, is all groundwork for a future mission. The better the pre-mission data, the more efficiently a spacecraft can use its limited time and resources once it arrives. What can we say with confidence about what a Uranus orbiter would find? Some things are nearly certain. The gravity science would constrain the interior structure significantly. The atmospheric probe would measure noble gas abundances and deep atmosphere composition for the first time. The magnetometer suite would characterize the magnetic field over a full range of Uranian rotations and seasons. The imaging systems would produce surface maps of the major moons that would reveal whether they have young, geologically active surfaces or ancient, heavily cratered ones. Other findings are more uncertain but scientifically plausible given what we already know. The moons may show evidence of subsurface oceans. If Miranda, the innermost major moon, has liquid water beneath its heavily fractured surface, that would reopen questions about what processes shaped its extraordinary landscape, which includes cliffs nearly 20 kilometers high, the tallest known cliffs in the solar system. The rings may show unexpected structure at high spatial resolution, with features that reveal the dynamics of material distribution in a way that constrains the age and origin of the ring system. Whether the rock giant hypothesis or the ice giant model turns out to be closer to the truth, the gravity data from an orbiter will push the answer significantly further toward resolution than anything currently available. There is also a broader scientific context worth noting. The history of outer solar system exploration is a history of surprises. Before Voyager 2 arrived at Uranus in 1986, the known moon count was 5. Voyager 2 found 11 more in a matter of hours. Before Cassini arrived at Saturn, Enceladus was thought to be a geologically dead ice ball. Cassini discovered active geysers of water vapor erupting from its south pole within months of arrival. Before Juno entered Jupiter's orbit, the planet's polar regions were thought to be broadly similar to the mid-latitudes. Juno revealed massive polygonal cyclone systems at both poles that had never been anticipated. The outer solar system has a reliable record of being far stranger and more complex than our best models predicted. Uranus has already demonstrated this pattern at a smaller scale. Every new instrument trained on it has revealed something unexpected. The storms, visible to amateur telescopes that Voyager 2 couldn't detect, the infrared auroras found after 30 years of searching, the hints of subsurface oceans on moons once thought to be inert ice balls, the possible recharacterization of the planet's internal composition entirely. The next surprise is almost certainly waiting. The launch windows in 2031 and 2032 represent a rare alignment of scientific readiness, political support, technical capability, and gravitational geometry. Planetary scientists have been building toward this moment for years, publishing the foundational studies, refining the orbital data, developing the instrument concepts. The Decadal Survey has provided the political endorsement within the scientific community. The Jupiter Gravity Assist is available only during those specific windows, and not again for an extended period afterward. Whether the mission actually launches depends on budget decisions that have not yet been finalized, and on the complex interplay of competing priorities within national space programs. But the scientific case has never been stronger, and the opportunity has rarely been clearer. In 1781, William Herschel looked through a telescope he had built by hand and discovered that the solar system was larger than anyone had known. 2 centuries later, a single spacecraft spent a few hours nearby and revealed that the planet he discovered was stranger than anyone had imagined. Now, 4 decades after that brief encounter, a new wave of science has revealed that it is stranger still, and that we have barely begun to understand it. A planet that rolls around the sun on its side. That may be mostly water or mostly rock, and we cannot yet say which. That is the coldest planet in the solar system, despite being the 4th most massive. That has a magnetic field pointing in directions no other planetary magnetic field points, whose moons may carry liquid water hidden beneath frozen surfaces, whose rings are darker than coal. This is not a world we understand well. It is a world we are only beginning, properly, to study. To understand what a Uranus mission would truly mean scientifically, it helps to understand where ice giant science currently stands in relation to the rest of planetary astronomy. The solar system contains 4 giant planets. Jupiter and Saturn are gas giants, composed overwhelmingly of hydrogen and helium, with rocky and metallic cores at their centers, but no solid surface. They are large, well-studied, and actively targeted by long-duration missions. Juno has been in orbit around Jupiter since 2016. Cassini orbited Saturn for 13 years, before being deliberately destroyed in 2017 by flying into the planet's atmosphere. The ice giants are different in structure and in degree of exploration. They are smaller than the gas giants, but still enormously larger than the terrestrial planets. Uranus has 4 times the diameter of Earth and 14.5 times its mass. Neptune is slightly smaller in size, but somewhat more massive, at about 17 times Earth's mass. Both have deep mantles of compressed water, methane, and ammonia, with pressures and temperatures that bear no resemblance to anything we experience on Earth. And yet, despite being the 2 outermost planets of the solar system proper, neither has been visited since Voyager 2's flybys. Neptune was passed on August 25, 1989, 3.5 years after the Uranus encounter. The 2 flybys together, each lasting just a few hours, represent the entirety of in situ ice giant science. Everything else has been done from Earth or from Earth-orbiting telescopes. This stands in sharp contrast to the inner solar system and to the gas giants. Mars has been orbited continuously since the late 1970s and is currently being studied by multiple orbiters and rovers simultaneously. Mercury has been orbited by 2 missions. Venus has been recently visited again after decades. Jupiter and Saturn have both hosted long-duration orbiters. The ice giants are the largest unexplored region in our planetary neighborhood. Part of the reason is trajectory. Getting to Uranus or Neptune efficiently requires either very long travel times or carefully timed gravity assists from the inner planets and Jupiter. The windows for gravity-assisted trajectories to the ice giants don't come around every year. And because these planets are so far from Earth, communications delays are severe, missions require autonomous capability, and the cold environment poses engineering challenges for instruments and power systems. The missions to the gas giants were, in retrospect, more tractable technically. Jupiter and Saturn are massive enough that they can be reached more quickly. They are close enough that communication delays are shorter, and the scientific case for those missions was easier to build because we had more pre-existing data about those planets. The ice giants have long paid a price for their distance and their apparent tranquility, but that apparent tranquility was illusory, and the scientific case for exploring them has been building for years. Comparative planetology, the study of planets as a group rather than individually, is one of the most powerful tools in understanding how planetary systems work. The diversity of our solar system's 8 major planets tells us something about the range of outcomes that the process of planetary formation can produce. Each additional data point, each planet for which we have detailed measurements, constrains the models more tightly. The gas giants have been studied extensively. The terrestrial planets have been studied extensively. The ice giants remain largely unknown, and these are the planets that most resemble the most common type of planet found orbiting other stars. Since the discovery of the first confirmed exoplanet in 1992, astronomers have discovered thousands of planets orbiting other stars. When you look at the size distribution of these planets, a striking pattern emerges. The most common planet sizes are those between Earth and Neptune. Rocky Earth-sized planets are common, but so are planets larger than Earth and smaller than Neptune, the so-called super-Earths and sub-Neptunes. The gas giants, the Jupiters and Saturns of other systems are actually less common than these intermediate mass planets. Our own solar system appears to be somewhat unusual in not having any planets in the size range between Earth and Neptune. We have rocky terrestrials up to about 1.5 Earth radii, and then a gap, and then ice giants at about 4 Earth radii, and then gas giants larger still. Most planetary systems don't have this gap. They are full of planets in the intermediate range. Understanding Uranus and Neptune, our 2 ice giants, and the closest things we have to the most common type of planet in the galaxy, is therefore not just important for understanding our own solar system, it is critical for understanding planets generally. What are these planets made of? How do their atmospheres form and evolve? How do they interact with their host stars? How do they generate magnetic fields? How do their moons form? The answers we get from studying Uranus up close will translate directly to interpretive frameworks for thousands of exoplanets we can never visit. This is part of why the rock giant hypothesis is so significant. If Uranus is much rockier than assumed, it challenges not only models of Uranus's formation, but models of ice giant formation generally. And if ice giant formation models need revision, that has implications for how we think about sub-Neptune exoplanets. The question of what Uranus is made of isn't purely a question about one planet in our own solar system. It is a question that echoes across the galaxy. When Voyager 2 arrived at Uranus, the imaging team expected to see a featureless blue ball. The instruments of 1986, observing a planet in southern summer with the pole pointed toward the sun, did reveal a planet with little visible structure in the part of the atmosphere that was illuminated. But this appearance was partly circumstantial. Uranus was at a seasonal configuration that minimized the appearance of atmospheric dynamics. The instruments were also less sensitive than modern equivalents by orders of magnitude. The world Hubble, Keck, and James Webb have revealed is a place with hurricanes the size of continents, with atmospheric circulation that changes dramatically with the seasons, with auroras dancing at unexpected latitudes, with rings as dark as asphalt, and with moons that may harbour hidden oceans beneath surfaces of fractured ice. The storms detected at the Keck Observatory in 2014 were a turning point in how the planetary science community thought about Uranus. 8 major storms, with the brightest accounting for 30% of the total reflected light at 2.2 microns wavelength. Amateur astronomers, with relatively modest equipment, were able to detect storm features that had never been visible before. This is not a quiet world. It is a world that had been hiding its dynamics behind the limitations of what we could see. Understanding the energy source for these storms is still an active area of research. On Jupiter and Saturn, the energy that drives large weather systems comes primarily from the slow release of interior heat. The storms are, in a sense, the visible signature of heat moving from deep inside the planet toward the atmosphere. Uranus, with its anomalously low internal heat flux, can't use this mechanism to the same degree. So where does the energy for the observed storms come from? One possibility is solar energy. Uranus absorbs solar radiation at its upper atmosphere, and this energy drives circulation. But the Sun is nearly 3 billion kilometers away from Uranus on average, and the amount of solar energy reaching Uranus is about 360 times less per square meter than reaches Earth. This is a very limited energy source for driving major weather systems. Another possibility is that despite the overall low heat flux, there are localized regions of the mantle or lower atmosphere where convection is more active, driven perhaps by chemical composition gradients or phase transitions in the compressed ices. These localized convective upwellings could inject energy into the upper atmosphere in concentrated bursts, creating the intense storms observed without requiring the planet as a whole to release significant heat. A third possibility involves the interaction between the solar wind, the magnetosphere, and the atmosphere. The research from Imperial College London showing that the solar wind heats the thermosphere directly suggests that energy input from the magnetosphere is a real and ongoing process. Whether this energy input is sufficient to drive the major storms, rather than just the aurorally heated thermosphere, remains an open question. The extreme axial tilt adds another layer of complexity. During the long polar summers, one hemisphere receives continuous illumination for decades, while the other sits in permanent darkness. The resulting temperature gradients must drive atmospheric circulation on timescales of years to decades. The Hubble observations tracking the accumulation of polar aerosols over 20 years show that this seasonal circulation is real and measurable. Whether it creates storm conditions similar to those observed at the Keck Observatory, or whether a different mechanism is responsible, cannot be definitively determined from Earth-based observations alone. A Uranus orbiter with a sustained observation program lasting at least one full Uranian year would be needed to fully characterize the seasonal dynamics. One Uranian year is 84 Earth years, so no spacecraft will observe a complete Uranian season cycle. But even a mission lasting 5 to 10 Earth years would capture a significant fraction of one season and provide data across multiple latitudes and longitudes that would allow scientists to build much more complete circulation models. The moons of Uranus deserve more attention than they typically receive in discussions of outer solar system science. Miranda, the innermost of the 5 major moons, is in some respects the most geologically fascinating world in the outer solar system. It is small, about 480 kilometers in diameter, slightly smaller than the asteroid Ceres, but its surface is unlike that of any other small world we know. Voyager 2 imaged about 45% of Miranda's surface during the 1986 flyby, and what it revealed was extraordinary. The moon's terrain is chaotically diverse, with regions of ancient, heavily cratered terrain sitting directly adjacent to far younger, less cratered terrain that shows deep grooves, ridges, and complex, layered structures. One region, called Verona Rupes, is a cliff face roughly 20 kilometers high. That is about 10 times the height of Yosemite Valley's El Capitan. It is the tallest known cliff in the solar system. Several competing hypotheses have been proposed to explain Miranda's fragmented surface. One early idea was that Miranda had been catastrophically disrupted by an impact and then gravitationally reassembled from the fragments, with different pieces settling back together in a chaotic arrangement. This would explain the jumbled terrain juxtapositions. However, this explanation has become less favored over time because the reassembly would likely mix the fragments thoroughly rather than creating the sharp boundaries between terrain types that Voyager 2 imaged. More recent thinking favors explanations involving tidal heating. Miranda, in the past, may have been in an orbital resonance with other Uranian moons that caused tidal forces from Uranus to flex and heat its interior. This tidal heating could have driven volcanic or tectonic activity on a geologically recent timescale, resurfacing some parts of the moon while leaving others untouched. This is similar to the process that keeps Io, one of Jupiter's moons, geologically active today, though Miranda's past activity appears to have been far less intense and is no longer ongoing. The 2025 studies suggesting possible differentiated interiors for the major Uranian moons, with rocky cores, possible liquid water oceans, and icy outer shells, would, if confirmed, provide a different mechanism for Miranda's unusual geology. If a liquid water ocean exists or recently existed beneath Miranda's surface, it could drive geological activity through a completely different mechanism than tidal heating alone. Cryovolcanism, the eruption of water or water-ammonia mixtures instead of silicate magma, could have resurfaced parts of Miranda geologically recently and might still be ongoing at some level. The question of whether Uranian moons have subsurface oceans hinges on several factors: the composition of the mantle ices, the amount of antifreeze compounds like ammonia that would lower the freezing point of water, the amount of internal heat generated by radioactive decay in the rocky core, and the pressure of the overlying ice column. For Earth's ocean moon Enceladus, it was direct observation of water vapor geysers by Cassini that confirmed the subsurface ocean. For Jupiter's Europa, decades of magnetic field measurements combined with surface imaging have built a compelling indirect case. For the Uranian moons, we have essentially no data relevant to the question, except the surface imagery from Voyager 2 and the composition constraints from remote spectroscopy. Ariel, the second innermost major moon, also shows signs of relatively recent geological activity in its Voyager 2 imagery. It has a smoother, less heavily cratered surface than the outer moons, with extensive valley networks that look like they were carved by some kind of fluid flow or tectonic stretching. Titania, the largest Uranian moon, shows long fault lines and canyon systems, visible even in Voyager 2's limited imagery. These features suggest that multiple moons in the system have had geological histories more complex than a simple frozen since formation story would allow. None of this can be confirmed without better data. The 2025 hints at differentiated interiors come from careful modeling and comparison with compositional constraints from remote spectroscopy. They are plausible. They are consistent with what we know. But plausible and consistent is not the same as confirmed. A Uranus orbiter would carry instruments capable of making direct compositional measurements of moon surfaces via spectroscopy, measuring the gravitational fields of the moons during flybys to determine their interior density distributions, searching for plumes or surface features indicative of cryovolcanism, and mapping the magnetic field environment near each moon to look for signs of electrically conducting liquid layers beneath the surface. These are standard tools of planetary moon science that have been applied at Jupiter and Saturn with remarkable success. At the Uranian moons, they have never been applied at all. The ring science is equally important and equally limited by current data. The 13 confirmed rings span a range of widths from a few kilometers to roughly 100 kilometers. They orbit Uranus in the same extreme equatorial plane as the moons, tilted nearly 98 degrees relative to the solar system's ecliptic. When Voyager 2 approached from the sunward side in 1986, the rings were nearly face-on, appearing as a nearly circular bullseye. Voyager 2 also observed the rings from the dark side as it departed, providing a different viewing geometry. The ring particles appear to be in a constant state of grinding and attrition. Ring particles collide with each other and with the small ring moons, generating fine debris that is swept away by various forces over time. The rings of Uranus are estimated to be actively losing material and may eventually dissipate entirely, though on timescales of millions to billions of years. The relative youth of the rings, estimated at only 600 million years, is consistent with them having formed from a single disruption event rather than being primordial. Understanding the ring dynamics requires knowing the masses of the ring-confining shepherd moons, the exact composition and size distribution of ring particles, and the long-term orbital evolution of ring material under the influence of both Uranus's gravity and radiation pressure from the Sunday. None of these can be measured precisely from Earth. A spacecraft passing through or near the rings would provide direct sampling data, and an orbiter could track ring particle motions over time with a precision no ground-based telescope can achieve. The occultation data from April 2025 will help constrain ring positions and potentially reveal narrow-scale ring structure that hasn't been detected before. But the full three-dimensional architecture of the ring system, its vertical structure, its particle composition, the precise relationship between ring features and ring moons, all require in situ measurement. There is one more aspect of Uranus science that deserves careful consideration, and that is the timescale of the scientific return. A Uranus orbiter launched in 2031 would take approximately 13 years to reach Uranus, arriving around 2044. That timeline accounts for the Jupiter gravity assist and the trajectory optimization available during the favorable launch window. In comparison, the Cassini mission to Saturn was launched in 1997 and arrived in 2004, 7 years later. Saturn is roughly twice as close to Earth as Uranus. Uranus is simply very far away. Once the spacecraft arrives, it would begin an orbital phase potentially lasting several Earth years. The orbital phase would include initial reconnaissance orbits at a safe distance, followed by gradually lower orbits for detailed atmospheric, magnetic, and ring science, and then a series of close moon flybys and potentially a final low-altitude atmospheric pass before the mission concludes. Planning is being done now, nearly a decade before launch, because the scientific objectives need to guide instrument selection, and instrument selection determines the mass and power budgets, which determine the spacecraft size, which determines the launch vehicle, which affects cost. The entire chain of decisions from science to hardware must be worked through carefully, and that process takes years. The 2025 occultation campaign was partly motivated by mission planning requirements. The 400-kilometer improvement in Uranus's orbital position is a concrete contribution to the navigation team that will plot the spacecraft's trajectory to arrive at the right place at the right time. Similar measurements over the coming years will continue to refine the orbital ephemeris to the precision needed for a successful rendezvous. A common question in science communication about outer solar system missions is why we should invest billions of dollars and decades of effort in studying a planet that most people rarely think about. The answers operate at multiple levels. The most fundamental is that understanding the solar system we live in is a form of understanding ourselves. The elements that make up every living thing on Earth were forged in the cores of stars and distributed through the galaxy by stellar explosions. Many of those elements arrived on Earth during the period of heavy bombardment early in the solar system's history, carried by icy bodies from the outer regions of the solar system that were deflected inward by gravitational interactions with the forming giant planets. Uranus, Neptune, and their families of moons were participants in the processes that made Earth habitable. Understanding how the ice giants formed and evolved is part of understanding the history of our own planet. At a more immediate level, the question of whether Uranian moons might harbour subsurface liquid water is scientifically and philosophically significant. Life on Earth exists wherever liquid water is present, from deep ocean hydrothermal vents to hypersaline lakes to the acidic clouds of volcanic regions. The consensus in astrobiology is that liquid water is a necessary condition for the kind of biochemistry that underlies all known life. If the Uranian moons have subsurface liquid water, they have, by that criterion, one of the known requirements for life. This doesn't mean anyone expects to find organisms living in the subsurface oceans of Uranian moons. The environments would be cold, dark, and under enormous pressure. But life on Earth exists in conditions that would have seemed impossibly hostile before they were explored. The deep ocean floor around hydrothermal vents was considered virtually uninhabitable until the 1970s. when submersibles discovered rich ecosystems thriving in near-total darkness, fed by chemosynthesis rather than photosynthesis. The possibility of life in outer solar system ocean worlds cannot be dismissed simply because conditions are extreme. Whether or not life exists anywhere in the Uranian system, understanding the Moon's interior water chemistry would teach us about the geochemical processes that occur in water-rock interaction environments under high pressure. These are conditions relevant not only to the question of habitable environments, but to understanding the chemistry of the early Earth before the surface became stable and the oceans formed. At a still more immediate level, the ice giants represent engineering and scientific challenges that drive development of new capabilities, building instruments that can operate at Uranian distances, where power from solar panels is negligible and nuclear power sources are required, where temperatures are extreme, where communication delays prohibit real-time control, where radiation environments differ from the inner solar system, pushes the boundaries of what spacecraft technology can do. The solutions developed for a Uranus mission will be applicable to future missions farther out, to the Kuiper Belt, to Neptune and its moon Triton, and potentially beyond the heliosphere into interstellar space. The 2031 launch window is not just a logistical convenience. It represents the alignment of decades of scientific preparation, technological development, and political will. The decadal survey's prioritization of the Uranus mission reflects a judgment by the scientific community that the time is right, the questions are compelling, and the instruments exist to answer them. What remains is the will to go. Uranus has been waiting for nearly 4 decades since Voyager 2's brief encounter. It will not get closer or more accessible. The ring system will not become easier to study from Earth. The moons will not reveal their interior structures through remote observation. The composition of the mantle will not be resolved by modeling alone. The only way to know what Uranus truly is, to resolve the rock giant question, to determine whether life could exist in its moon system, to understand how its uniquely distorted magnetic field works, to characterize the dark, narrow rings that have defied explanation for half a century, is to go there. The window opens in 2031. What happens next is a decision still being made. There is a peculiar quality to Uranus as a subject of scientific inquiry that rarely gets acknowledged. It is the planet that rewards patience. Most of what we've learned about Uranus in the last decade came not from new missions, but from looking harder at what we already had. Jasinski's reanalysis of Voyager 2 magnetic field data in 2024, nearly 40 years after the flyby, changed our understanding of the magnetosphere's structure. The infrared aurora detection in 2023 came after 30 years of advances in detector technology applied to the same observational problem. The 2025 studies on interior composition came from taking existing observational constraints and applying more sophisticated modeling frameworks to them. The 2025 Hubble results on atmospheric dynamics came from 2 decades of accumulated images taken by a telescope launched in 1990. None of this required a new spacecraft. All of it required sustained, careful attention to a planet that had been largely overlooked. This is not a criticism of how the scientific community has prioritized resources. It is an observation about the nature of science. The instruments we build and the missions we fly define a certain envelope of what can be measured. Within that envelope, discovery doesn't stop when the mission ends. It continues as long as scientists keep asking new questions of existing data, keep building better analytical tools, and keep developing theoretical frameworks that can extract more meaning from the same observations. Voyager 2 collected data at Uranus for a few hours in January of 1986. In the 4 decades since, scientists have been gradually mining that dataset, extracting new understanding with each new technique. The magnetosphere paper published in Nature Astronomy in 2024 is remarkable precisely because it came from data collected nearly 40 years earlier. The scientists who collected that data could not have anticipated the question Jasinski's team would eventually ask, or the analytical methods they would use to answer it. This is the cumulative nature of scientific progress. Observations made in one era often yield their deepest insights only when examined with the tools and questions of a later one. Uranus itself is patient in a different way. It moves through its 8-4-year orbit with the unhurried regularity of an object governed purely by physics. Its north pole will reach summer in 2030, beginning the long polar day. Its rings will continue their slow dissipation over millions of years. Its moons will maintain their tilted orbits, carrying their hidden interiors through the cold darkness of the outer solar system. 40 years between visits is a long time for science. It is barely a pause on Uranus. The planet's discovery in 1781 came during a period when the nature of planets, comets, and the structure of the solar system were all active areas of fundamental debate. Newton's mechanics had been established for nearly a century, but the application of those mechanics to the precise description of planetary orbits was still being refined. The discovery that the solar system extended far beyond Saturn, that another planet had been circling the Sun undetected while civilizations rose and fell on Earth, was a conceptual shock. Within 60 years of the discovery of Uranus, the anomalies in its orbit had been noticed and analyzed. The planet was not exactly where Newtonian mechanics predicted it should be. Something was pulling on it from beyond. Two mathematicians, John Couch Adams in England and Urbain Le Verrier in France, independently calculated where that something should be, based on the gravitational perturbations of Uranus's orbit. When telescopes pointed to the predicted position in 1846, Neptune was found within 1 degree of the predicted location. This was one of the greatest triumphs of mathematical physics in history. A planet was predicted from pure mathematics, from the anomalies in another planet's motion, and then discovered exactly where the equations said it would be. The chain of reasoning from Uranus's irregular orbit to Neptune's discovery is one of the clearest demonstrations that mathematics describes physical reality in a precise and predictive way. Uranus led us to Neptune, and now, nearly 2 centuries later, Uranus is leading science toward a new phase of discovery. The rock giant hypothesis, the subsurface ocean suggestions for the moons, the revised magnetosphere models, the seasonal atmospheric dynamics measured by Hubble, the infrared auroras detected by Keck, all of these are pointing toward a planet that is more complex and scientifically valuable than its relative neglect would suggest. The comparison to Neptune is instructive in another way. Neptune has its own set of scientific mysteries. It emits significantly more internal heat than Uranus, despite being broadly similar in composition and formation history, which raises questions about why the two planets are so different in thermal behavior when they seem so similar in other respects. Neptune also has Triton, a large moon that orbits in the retrograde direction, moving opposite to Neptune's rotation. Triton is almost certainly a captured Kuiper belt object, a body that originated in the outer reaches of the solar system and was gravitationally captured by Neptune. Triton is geologically active, with nitrogen geysers erupting from its surface, and it is gradually spiraling inward toward Neptune, destined to be torn apart by tidal forces in roughly 3.5 billion years to potentially form a new ring system. None of this has been observed since Voyager 2's 1989 flyby. Like Uranus, Neptune and its moon system have been studied only from Earth and from Earth-orbiting telescopes in the more than 3 decades since. The ice giants, taken together, are the largest gap in our systematic exploration of the solar system. They are the 2 remaining major planets that have never hosted a dedicated orbiting spacecraft. They are the 2 planets whose internal structures are most uncertain. They are the closest analogues to the most common type of planet found in other stellar systems. A Uranus orbiter, if launched in the 2031 window, would not only advance our understanding of Uranus specifically, It would open a new era of ice giant science that addresses fundamental questions in planetary formation theory, comparative magnetosphere physics, astrobiology, and our understanding of the most common planetary environments in the galaxy. The scientific returns from the Cassini mission to Saturn demonstrate what is achievable. Before Cassini, Saturn was reasonably well characterized in broad terms. After 13 years in orbit, the mission fundamentally transformed our understanding not only of Saturn, but of planetary rings, moon geology, the potential for habitability in ocean worlds, and the dynamics of magnetospheres. The discoveries at Enceladus alone, the active geysers, the subsurface ocean, the organic chemistry in the plume material, changed the criteria used in planning future astrobiology-focused missions. A Uranus orbiter has the potential to produce an equivalent transformation. The unknowns are larger because the starting point of knowledge is lower. The rock giant versus ice giant question is not a minor refinement. It is a fundamental uncertainty about what the planet is made of. The magnetic field geometry is not just unusual. It may require a completely new framework for understanding ice giant dynamo processes. The moons are not just undercharacterized. Some of them may turn out to be ocean worlds that no one had seriously considered as candidates until the most recent modeling. Consider the potential sequence of events. A Uranus orbiter launches in 2031 and arrives around 2044. Initial gravity science measurements constrain the interior structure within the first year. Atmospheric probe data establishes noble gas abundances and refines compositional models. Magnetometer data begins building the three-dimensional picture of the magnetic field. Initial moon flybys produce high-resolution images and spectral data that are unambiguous about surface composition. Then, as the mission proceeds, more subtle science builds. Repeated flybys of Miranda begin to reveal whether its terrain reflects a cryovolcanic history or something else. Thermal emission measurements of Ariel and Titania constrain subsurface heat flow. If any of the moons shows plume activity, the mission profile might be adjusted to investigate it directly. The ring system is mapped in 3 dimensions. The seasonal changes in the atmosphere are tracked over years. By the mission's end, sometime in the late 2040s or early 2050s, the question of what Uranus is made of will have an answer. The question of whether the moons harbour subsurface oceans will have an answer. The magnetic field will be understood in context. The rings will be characterized. The atmosphere will be modelled with sufficient data to project its behaviour across full seasons. These are not incremental advances. They are the transformation of a fundamentally unknown world into one that is scientifically well understood. The transformation that Cassini achieved for Saturn, the transformation that Galileo achieved for Jupiter, the transformation that would have occurred for Uranus 40 years ago if Voyager 2 had been an orbiter rather than a flyby. We are approaching the point at which that transformation can finally happen. The planet itself will be ready. In 2031, as the spacecraft departs, Uranus will be approaching northern summer, with the North Pole increasingly illuminated. By the time the spacecraft arrives in 2044, Uranus will be well into its long polar summer, the atmosphere responding to decades of continuous illumination at the northern pole. It will be the most scientifically interesting phase of the Uranian season cycle, and a spacecraft in orbit would have front-row access to the planetary dynamics unfolding in real time. There is a reasonable probability that some of what a future orbiter finds will be surprising in ways we cannot currently anticipate. The history of outer solar system exploration makes this almost a certainty. Voyager 2's few hours at Uranus produced 11 new moons and a fundamentally weird magnetic field. Cassini's arrival at Saturn produced geysers on Enceladus. New Horizons revealed a geologically active surface on Pluto, with nitrogen glaciers flowing toward a basin the size of Texas. Every outer solar system world we've visited in detail has harbored surprises that existing models had not predicted. Uranus has been telling us, through every new observation, that it is stranger than we thought. The tilt, the cold, the weird magnetic field, the possible internal insulation from an ancient collision, the hints of ocean worlds in its moons, the dark rings that shouldn't be as narrow as they are. These are not the characteristics of a planet we understand. They are the characteristics of a planet asking questions. And they are questions that matter, not only for understanding a single world in the outer solar system, but for understanding how planets form, how they evolve, what makes some worlds potentially habitable and others inhospitable, and what the most common kind of planet in the galaxy is actually like on the inside. Uranus has waited nearly 40 years for someone to come back. The scientific case for returning has never been stronger. The technology to do it exists. The window in 2031 and 2032 represents the clearest opportunity in a generation. What happens in that decade may determine how much we understand about one of the most common types of world in the universe, and whether the solar system's most overlooked planet finally receives the sustained scientific attention it has for so long deserved. To appreciate how much Uranus science has changed in just the last 10 years, it helps to sit with the sheer scale of what we still don't know, and trace how quickly some of those unknowns have shifted. A decade ago, a planetary scientist asked about Uranus's internal heat would have simply stated the problem. The planet radiates barely more energy than it receives from the sun, and nobody knows exactly why. That was the answer, a shrug embedded in a number. Today, that same scientist would point to the 2025 studies, describe the high-entropy insulating shell model derived from the impact simulations, connect it to the collision hypothesis tested against 50 different modelled scenarios, and explain how the shell's existence is consistent not only with the low heat flux, but with the magnetic field geometry and the observable structure of the atmosphere. The shrug has become a mechanism, not confirmed, but physically coherent. That is not a minor shift. That is the difference between a mystery and a hypothesis. And hypothesis is where science begins to move. The same thing has happened with the atmospheric dynamics. In 2015, a scientist asked about Uranian weather would have described a calm, nearly featureless planet with occasional cloud formations. By 2025, the same question produces descriptions of continent-sized storms bright enough for amateur telescopes to detect, of aerosols accumulating at the poles in response to seasonal illumination, of a thermosphere being heated by the solar wind in a way seen nowhere else in the solar system. Each of these developments came from a combination of better telescopes, better analysis, and sustained scientific attention directed at a planet that historically attracted rather little of it. The James Webb Space Telescope added new spectroscopic resolution. The Keck Observatory added infrared imaging capability. Hubble provided 2 decades of time-lapse comparison data. None of these instruments were built specifically to study Uranus. They were built to study the broader universe, and Uranus benefited because it was there and because scientists pointed them at it. Imagine what a spacecraft designed specifically to study Uranus could do. The case of Enceladus is instructive. Before Cassini, the Moon was a small, icy body about 500 kilometers across orbiting Saturn at moderate distance. It had been imaged by Voyager 2 in 1981, revealing a partially cratered, partially smooth surface that suggested some geological activity, but nothing extraordinary. In 2005, Cassini's magnetometer detected an anomaly near Enceladus's south pole. The spacecraft was redirected for a closer pass. It found geysers of water vapor and ice particles erupting from linear fractures in the south polar terrain. Subsequent passes flew directly through the plumes, sampling the material being ejected. The plume material contained water vapor, sodium chloride, silica particles, molecular hydrogen, and organic compounds. The molecular hydrogen, in particular, indicated ongoing chemical reactions between water and hot rock in a subsurface hydrothermal environment. The same kind of chemistry that powers deep ocean hydrothermal vents on Earth. This small, previously unremarkable moon turned out to have an active subsurface ocean that is interacting geochemically with its rocky core in a way that is, by every current measure, potentially hospitable to microbial life. Cassini didn't find life on Enceladus. It found the conditions that, on Earth, are associated with life. That is a profound and genuinely unexpected discovery, made possible because a spacecraft was in orbit around Saturn with the right instruments and the flexibility to redirect its science program when unexpected signals appeared. The Uranian moons may hold equivalent surprises. Miranda's extraordinary topography has never been adequately explained by any model. The hypothesis that it was shattered and reassembled was replaced by the tidal heating hypothesis, which has now been partially supplanted by newer models incorporating possible cryovolcanism driven by a subsurface ocean. None of these hypotheses has been tested against direct observational data from Miranda's surface, interior, or thermal environment. Voyager 2 saw roughly half of Miranda's surface from a distance. That's all anyone has ever seen. Ariel's smooth terrains and extensive valley systems suggest geological resurfacing at some point in its history. Titania's fault scarps indicate past expansion or contraction of the interior. These are all signs of geological activity that cannot be explained simply by a primordial frozen body radiating heat away into space. Something heated these moons. Whether that something was tidal forcing, radioactive decay, impact events, or the thermal consequences of their formation, the answer has implications for how geologically active the outer solar system is, and whether the conditions for habitability are more widespread than currently assumed. The moons of Uranus are named after characters from Shakespeare and Alexander Pope, Miranda and Ariel from The Tempest, Umbriel from The Rape of the Lock, Titania and Oberon from A Midsummer Night's Dream. The smaller, irregular moons draw on an extended literary cast: Caliban, Sycorax, Prospero, Setebos, and Stefano from Shakespeare's The Tempest. Trinculo and Francisco from The Tempest as well. Puck and Mab from A Midsummer Night's Dream. Margaret from Much Ado About Nothing. Ferdinand from The Tempest, and from The Tempest of Life's Greater Concerns. The naming convention makes Uranus's moon system the most literarily inclined address in the solar system. Every other planet draws its moon names from mythology. Uranus draws from Shakespeare. There is something fitting about this. For a planet that has been chronically underestimated, poorly resourced in terms of mission attention, and consistently more interesting than its reputation would suggest. The characters from The Tempest are, among other things, inhabitants of an island that nobody visits, with secrets that only the most committed observer is willing to uncover. The ring system also has a naming convention that reflects the history of discovery. The first 9 rings were designated with Greek letters: 6, 5, 4, alpha, beta, eta, gamma, delta, and epsilon. The order reflects the order in which they were identified from occultation data, which does not correspond neatly to their distance from Uranus. The 2 rings discovered by Voyager 2 were named the Zeta ring and the Lambda ring. The 2 outer rings, discovered by Hubble in the early 2000s, announced in 2025 after confirmation, were designated the Mu ring and the Nu ring. The Epsilon ring is the brightest and most substantial and the most studied. It has a narrowness that defies simple explanation. Under the laws of orbital mechanics, ring particles at slightly different orbital radii travel at slightly different speeds and gradually spread apart over time. The Epsilon ring should be much wider than it is. The shepherd moon, Cordelia, orbits just inside it, and Ophelia just outside. And it has long been argued that the gravitational influence of these 2 moons confines the ring material. The mechanics of this shepherd moon confinement have been modelled extensively, but the models have struggled to fully account for the ring's narrowness and for the distribution of material within it. Getting the dynamics right requires knowing the masses of Cordelia and Ophelia to greater precision than current data allows. And measuring those masses requires the kind of repeated, close observation that only an orbiting spacecraft can provide. What does it feel like to be a planetary scientist working on Uranus right now? There are scientists who have built entire careers on problems that may not be solvable without a dedicated mission. The internal structure team at the University of Zurich, working on the rock giant versus ice giant question, has essentially done everything possible with remote data and modelling. They have identified the uncertainty, quantified its range, and shown what kind of measurement would resolve it. They are waiting for a mission. The magnetosphere researchers, who published in Nature Astronomy in 2024, spent years extracting new understanding from nearly 4 decades old data. They too are waiting. The teams studying the moons know that the 2025 hints at subsurface oceans require close-range geophysical measurement to confirm or refute. They are waiting. The window in 2031 is, for these scientists, a lifeline attached to a clock. The launch window doesn't stay open forever. The Jupiter gravity assist that makes the trajectory feasible is available only during specific planetary alignments. If the mission doesn't launch during that window, the next feasible opportunity is years away, and the trajectory would be longer and more demanding. In planetary science, careers are measured in mission timescales. A researcher in their early 30s today could, if a mission launches in 2031 and arrives in 2044, spend the prime of their scientific career working with the first orbital data from Uranus. A researcher in their 40s might contribute to the mission design and then analyze the early orbital results. For some, the wait has already been a career. The 2025 occultation campaign illustrated both what is possible with current ground-based resources and what requires something more. 30 astronomers at 18 observatories achieved something remarkable. They improved the orbital position of Uranus by 400 kilometers. They coordinated more simultaneous observatories than any previous Uranus campaign in history. They demonstrated international scientific collaboration working at its best. And the result was a positional refinement that brought the target into sharper focus for a spacecraft that hasn't been built yet, toward a launch that hasn't been approved yet, arriving at a planet that has not been visited since the Challenger disaster year. There is a patience in science that mirrors the patience in the objects it studies. Uranus moves through its 8 4-year orbit, regardless of whether we're watching. Its moons circle in their extreme tilted plane whether or not we've sent probes to measure their gravity fields. The ancient collision that tipped the planet on its side happened roughly 3.5 billion years ago, and the insulating shell it deposited in the mantle has been trapping heat ever since. Through the entire history of complex life on Earth and the entirety of human civilization, the universe does not wait for us to be ready, but the optimal alignment of launch windows, scientific preparedness, and political priority is, in 2031, closer than it has ever been. There is something worth saying about what Uranus represents as a scientific object, specifically because of how strange it is. In physics, anomalies are valuable. A planet that behaves exactly as standard models predict teaches us nothing beyond confirming the model. A planet that refuses to fit tells us where the models are incomplete. Uranus's refusal to fit is comprehensive. It refuses to have a normal axial tilt. It refuses to release its internal heat normally. It refuses to center its magnetic field in the usual place. It refuses to have a simple, well-understood composition. Its moons refuse to be geologically inert as small, cold, distant objects are supposed to be. Each refusal is a constraint. Each anomaly marks a boundary of current understanding. The rock giant hypothesis is valuable precisely because it was not predicted. If Uranus turns out to be mostly rock, Something in our formation models is wrong, and figuring out what is wrong will teach us something real about how planets form. The insulating shell model for the low heat flux is valuable because it connects a physical anomaly to a specific historical event and makes testable predictions. If the model is correct, the interior structure of Uranus should show the signature of that shell in its density profile. A gravity science instrument in orbit would detect it. If the model is wrong, the data will show something inconsistent with a shell, and a new explanation will be needed. Either outcome advances understanding. The magnetosphere anomaly is valuable because it cannot be explained by standard dynamo theory, and therefore points towards something we don't understand about how ice giant magnetic fields are generated. Whatever that something is, it probably applies to Neptune as well, and to sub-Neptune exoplanets throughout the galaxy. Science advances fastest at its edges, where the anomalies live. Uranus is edge territory. It has been poorly explored, but it has not stopped asking hard questions just because no one was listening closely enough to hear them. The instruments that detected the infrared auroras in 2023 could not have existed in 1986. The modeling tools that Morph and Held used to explore the compositional parameter space of Uranus in 2025 could not have run on 1986 hardware. The 20-plus years of Hubble atmospheric imaging that revealed the polar aerosol dynamics had to be collected before anyone could analyze it. These advances took time because science takes time, but the advances have accumulated. And now, with better tools than have ever existed for studying the outer solar system, the picture of Uranus emerging from the data is both more complex and more tractable than it was when Voyager 2 sped past in January 1986. A planet rolled onto its side by a primordial collision, sealed inside its own heat by the insulating shell that collision left behind, generating a magnetic field from somewhere off-center in its mantle, surrounded by dark, narrow rings, 29 moons, and decades of accumulated scientific questions. That is the Uranus waiting at the other end of the 2031 launch window. It has been waiting a long time. The questions have been accumulating. The scientific case has never been stronger. The window opens in 5 years. There's a moment that comes up repeatedly in the history of planetary science, and it never stops being surprising. It is the moment when a spacecraft arrives at a world we thought we understood, and the data immediately starts contradicting what we expected to find. It happened at Pluto in 2015. New Horizons swept past after a 9-year journey and found, instead of the cold, dead, inert surface everyone had mentally modelled, a geologically active world with nitrogen glaciers slowly flowing toward a vast basin, towering mountains of water ice, and a haze-layered atmosphere far thicker and more complex than the models predicted. Nobody had predicted nitrogen glaciers on Pluto. The models weren't wrong in spirit. They were wrong in detail, in ways that turned out to matter enormously. It happened at Enceladus, at Titan, at Io, at almost every outer solar system body that has received sustained spacecraft attention. The outer solar system has a consistent record of being stranger than we assumed it would be, and more interesting for being so. Uranus hasn't had its Pluto moment yet. It hasn't had its Enceladus moment. It got a Voyager 2 flyby that lasted a few hours and produced foundational data that scientists are still analyzing 4 decades later, but data that was always too sparse to provide the kind of comprehensive picture that sustained orbital observation produces. The strangest thing about Uranus's position in planetary science isn't its axial tilt, or its cold atmosphere, or its off-center magnetic field. The strangest thing is that this planet, which is clearly unusual and clearly scientifically significant, hasn't had a dedicated mission since the mid-1980s. The Cassini mission cost roughly $3.3 billion and produced scientific returns that most planetary scientists consider one of the greatest investments in space science history. The Juno mission at Jupiter, still returning data as of 2025, costs roughly $1.1 billion and has fundamentally changed our understanding of Jupiter's interior, atmosphere, and polar regions. A Uranus orbiter and probe mission is expected to cost roughly $4 billion based on current estimates, depending on the final configuration, spread over the decades of development, launch, transit, and operations. That is a substantial investment, but comparable to what other flagships have cost. And the scientific return from a Uranus orbiter, if it produces anything like the surprises that Cassini, Juno, and New Horizons produced, would be extraordinary. The rock giant question alone, if answered, would rewrite planetary formation textbooks. The subsurface ocean question for the moons, if answered positively, would add several new worlds to the list of potentially habitable environments in the solar system. The magnetosphere question, if resolved, would provide the first empirical framework for understanding ice giant magnetic fields, with direct relevance to the thousands of sub-Neptune exoplanets being characterized by the James Webb Space Telescope and future missions. These aren't speculative returns. They are the natural scientific consequence of answering questions that current data cannot answer. The launch window in 2031 has a quality of urgency precisely because of what it makes possible and what missing it would cost. The Jupiter Gravity Assist available during that window shortens the transit time significantly. Without it, a spacecraft launched a few years later on a direct trajectory would take several years longer to arrive, shifting the arrival year from the mid-2040s into the early 2050s and reducing the total mission duration possible before funding constraints typically force a mission's end. Time in orbit at Uranus is scientifically precious in a way that isn't obvious from the outside. Each orbital period at Uranus is long because the planet is far from the Sun and any orbit around it is large. Getting multiple flybys of individual moons, covering the full longitudinal range of the planet's atmosphere, mapping the magnetic field over multiple Uranian rotation periods, all require time. The more time a spacecraft can spend in orbit, the more complete the scientific picture becomes. Every year of delay in launch is a year less of science at the target. This is not unique to a Uranus mission. It applies to every outer solar system flagship. But Uranus, having waited 4 decades already, has a particular urgency to its scientific case. The questions that have accumulated since 1986 are not getting smaller. They are growing. Each new observation that reveals something unexpected adds to the list of things a dedicated mission would need to investigate. There are currently scientists at universities and research institutions on multiple continents who have spent years developing instrument concepts, working out orbital architectures, modeling probe entry trajectories, and estimating measurement precision for a Uranus orbiter. This work is not abstract. It is specific, detailed, and technically rigorous. These researchers know which instruments would answer which questions. They know how long the spacecraft would need to spend in different orbital configurations to achieve different scientific objectives. They have done the engineering analysis on how to keep instruments warm and operational in the deep cold of the outer solar system, far from the sun's warming radiation. Some of these researchers have been working on this mission concept for more than a decade without a confirmed launch. They are building toward a mission that may or may not be approved on a timeline they cannot fully control. This is the normal condition of planetary scientists working on large, flagship missions. It requires a kind of sustained professional commitment that is sometimes described as a vocation more than a career. The alternative to a dedicated mission is continued study from Earth-orbiting telescopes, and from opportunistic analysis of old data. This approach has produced remarkable results, as the last decade of Uranus science demonstrates. But it has inherent limits. Stellar occultations happen only when the geometry cooperates. Hubble and James Webb can characterize the upper atmosphere and ring structures but cannot directly sample them. Modeling can explore parameter space, but cannot replace measurement. The 2025 moment in Uranus science, with its flurry of publications and the major occultation campaign, is perhaps best understood as a collective scientific argument being made to the broader community and to the funding agencies. Look how much we've learned from inadequate resources. Imagine what we could learn with the right ones. That argument is being made in the right language. The Decadal Survey has heard it. NASA's Planetary Science program has heard it. The Chinese National Space Administration's interest in a parallel mission to Uranus reflects that the argument has been heard internationally as well. Something shifted in the way Uranus is perceived in the scientific community over the last decade. It moved from the forgotten ice giant, the butt of a joke that gets in the way of serious discussions about Jupiter or Saturn, to the scientific priority of the decade. That shift was earned through sustained, careful, resource-constrained research that kept finding new things in old data and kept revealing that the planet was more interesting, more anomalous, and more scientifically important than its historical neglect suggested. The scientific community built that case deliberately. The occultation campaigns, the Hubble time series, the James Webb observations, the impact simulations, the interior structure modeling, the magnetosphere reanalysis. These were not random curiosity-driven investigations. They were coordinated efforts to understand a planet well enough to justify the commitment of flagship mission resources to it, and to ensure that a future mission, when it comes, would be designed to answer the right questions. That preparation is now largely complete. The questions are defined. The measurements needed to answer them are identified. The instruments capable of making those measurements exist or are in development. The trajectory that gets a spacecraft there efficiently opens in 2031. Uranus has been in the outer solar system for 4.5 billion years. It has been known to science for 245 years. It has been visited once, briefly, 40 years ago. The next chapter is being written by the scientists working today, training every available telescope at a blue-green dot rolling sideways around the Sun, waiting for the window to open and building the case, year by year and paper by paper, that the seventh planet deserves the sustained scientific attention it has always warranted and never fully received. The window opens in 2031, 5 years from now. The scientists are ready, the instruments are designed, the orbital mechanics are favourable. All that remains is the decision to go. There is a phrase used occasionally in planetary science that captures something important about how exploration actually works. The phrase is the cost of not knowing. It refers to the compounding scientific debt that accumulates when a major question goes unanswered long enough that all the adjacent research has to be conducted with a placeholder, where a real answer should be. The internal composition of Uranus is one of those placeholders. For decades, planetary formation models have been parameterized around an assumption that Uranus is an ice giant, mostly water, ammonia, and methane in its mantle, with a small, rocky core. That assumption has been embedded in models of solar system formation, in frameworks for understanding exoplanet interiors, in theoretical work on how magnetic fields form in ice giant conditions. An enormous structure of secondary research has been built on a foundation that, as of 2025, is formally uncertain in ways that the field only recently began to acknowledge. If Uranus turns out to be predominantly rocky, a significant fraction of that secondary research will need revision. Models that assumed an ice-dominated interior will have to be rebuilt with different compositions. The solar system formation scenarios that produce the standard ice giant picture will need adjustment. The frameworks for interpreting sub-Neptune exoplanet interiors will face new uncertainty. None of this is catastrophic. Science regularly revises its assumptions, but the revision is more costly when it comes decades after the assumption became embedded in multiple lines of downstream work. Getting the answer now, before the placeholder becomes even more structurally load-bearing, is itself scientifically valuable beyond the direct answer to the composition question. The same logic applies to the magnetic field. The current framework for understanding planetary magnetic field generation, the core dynamo model, works extremely well for Earth, Jupiter, Saturn, and the Sunday. It fails to describe the magnetic fields of Uranus and Neptune without significant modification. Planetary scientists have been working around this for 4 decades, essentially saying that ice giants must generate their fields differently, perhaps in the mantle, perhaps through processes affected by the high-entropy shell, and building around this uncertainty without resolving it. A magnetometer suite in orbit around Uranus, tracking the magnetic field over years as the planet rotates and as the solar wind pressure varies, would provide the data needed to either confirm the mantle dynamo hypothesis or point to an entirely different mechanism. Either outcome would be foundational. A confirmed mantle dynamo model would have immediate implications for how we interpret the magnetic field measurements of sub-Neptune exoplanets made by future missions. A refuted model, and a new one needed in its place, would be even more significant. These are not exotic scientific luxuries. They are basic physical questions about one of the 2 remaining unexplored planets in our solar system, with direct implications for the most common type of planet in the galaxy. The scientific culture around Uranus has also been changing in ways that matter. The field of Uranus science has historically been small. The number of researchers whose primary focus is Uranus is far smaller than those working on Mars, Jupiter, or Saturn. This is partly a consequence of the limited data available and partly a consequence of mission priority. Fewer missions mean fewer opportunities for early career scientists to build careers around Uranus-specific questions, which means fewer established researchers training the next generation of Uranus scientists. This is changing. The decadal survey's prioritization of a Uranus mission has attracted new researchers to the field. The 2025 publication surge reflects a growing community actively working on Uranus problems. The occultation campaign demonstrated international coordination capacity that the field didn't have a decade ago. The scientific infrastructure for a serious flagship mission is being built now, in advance of the mission itself. In a very real sense, the Uranus science community is preparing for an influx of data it has never experienced. A Uranus orbiter would produce more information about the planet in its first year than has been collected in the entire history of observation. Managing, processing, and scientifically interpreting that data requires a community trained to work with it, with the theoretical frameworks, analysis tools, and institutional knowledge to extract meaning from what will be an unprecedented dataset. That community is being built. It is being built by researchers writing papers about Uranus interior models who don't yet have the data to confirm them, by teams developing instrument proposals for a mission concept that hasn't been formally approved, by graduate students writing theses on Uranian atmosphere dynamics, magnetosphere behavior, and ring physics, knowing that the most important data won't arrive during their doctoral work, but that their work will matter when it does. The preparation is the investment. The mission, when it comes, lands in a field that has been thinking seriously about Uranus for years, with researchers who know what to look for and how to look for it. This is the scientific infrastructure that makes flagship missions productive, and it doesn't build itself. It requires the sustained investment of time, institutional support, and intellectual energy from a community that believes the question is worth answering before the data exists to answer it. The question is worth answering. A planet that may not be what we think it is, that generates a magnetic field from a location, and in a geometry we don't fully understand. That is the coldest place of all the planets in the solar system, despite being the 4th most massive. That experienced a collision 3.5 billion years ago so violent, it tipped it onto its side and left an insulating shell inside it that has been trapping heat ever since. that is surrounded by moons which, despite being small and cold and distant, may carry liquid oceans beneath their surfaces. That has rings darker than any other material we know, narrow in ways that confound explanation, made of something that hasn't been directly identified. This is not an ordinary planet, and 245 years after its discovery, 4 decades after the only spacecraft ever to visit it, left behind a dataset that scientists are still mining, the Uranus science community is closer to genuinely understanding it than at any point in history. The observations are sharper, the models are more sophisticated, the questions are better formulated, the instruments are ready, the launch window is 5 years away, and the planet itself, rolling along its 97.77-degree tilted axis, moving through the cold dark at over 6 kilometers per second in its orbit around the Sun, is waiting exactly where the mathematics says it will be. Consider one final thing. When Voyager 2 passed Uranus in January of 1986, the team at the Jet Propulsion Laboratory gathered around their screens to watch the data arrive. The light travel time from Uranus was about 2.5 hours. Every image, every magnetic field reading, every atmospheric pressure measurement came from a machine that had been traveling for 8.5 years to get there, transmitting at what we would now consider extraordinarily slow data rates across the largest distance that any human-made object had yet traveled from Earth. The team knew they had one shot. There was no second pass. There was no slowing down. Voyager 2 was moving at about 15 kilometers per second relative to Uranus and could not decelerate. The flyby lasted a few hours. Whatever was in the data would be all they had. What they got was extraordinary, and yet 4 decades of analysis later, it turns out to have been barely a first look. The magnetic field data raised questions that took 38 years to partially answer. The atmospheric images showed a world that appeared calm in a way that concealed the storms now visible in infrared. The moon images covered only fractions of the surfaces, leaving interiors entirely unmeasured, and geological histories entirely unresolved. In the time since Voyager 2's visit, the Hubble Space Telescope has been launched and has operated for 3 decades. The Keck Observatory has come online with adaptive optics that see through atmospheric distortion. The James Webb Space Telescope has revolutionized infrared astronomy. And still, the fundamental questions persist. Still, scientists are asking what Uranus is made of, how its magnetic field really works, and whether life's conditions exist somewhere beneath the frozen surfaces of its moons. The questions that Voyager 2 opened are still open. The window that 2031 offers is real. The scientific case has been built, observation by observation, paper by paper, by a community that has been working in the long gap between that first brief visit and whatever comes next. Whatever comes next begins with a decision still being made. The window is open for 5 years. The planet doesn't know we're watching. It has been rolling sideways around the Sun for 4.5 billion years. It will keep rolling regardless of what we decide. The questions we're asking are ours. So is the decision about whether to answer them. And when that window finally opens, everything we have learned in the long wait will be ready.